Broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to Burt Process Equipment's educational webinar on pH system design. I am Mark Girgenti, the Director of Design Engineering for Burt Process Equipment, and I want to welcome you all today to this educational webinar. Michael Offord from our group will be joining me as well. He'll be facilitating the questions. If you guys have any questions, please feel free to type them into the questions or the chat section, and we'll try to address all questions on the air. If we do not, then we will follow up at the end. There will also be time at the end for questions, and we will answer any questions that are unanswered with an email afterwards. There will be a couple of poll questions posted during the presentation. They're completely optional if you guys would like to participate. They just kind of address some of the topics we're going to be talking about today. In addition, there will be a brief survey sent out at the end of the broadcast. If you want to complete that, we're always interested in your feedback on our webinars and topics you'd like to see in the future. So without further ado, pHneutralization system is an important element of treating water in industrial laboratory facilities. Essentially, if you have a building, whether it's a lab space, semiconductor fab, pharmaceutical, general industry, even aerospace, really anything that you're going to be handling some kind of a chemical-based waste in, you're probably going to need to discharge that, and you're going to need to treat it prior to discharge to allow for in-compliance discharge to your local municipality, or municipality. And really, at the end of that system is you have a pHneutralization system, and the pHneutralization system is designed to treat the aqueous waste that comes in from the various applications. And when talking about a pHneutralization system, we're going to kind of start very high level in this conversation. We're going to kind of start talking a little about pH, starting pH, initially, some of the components that go into the system, some designs, standard designs, but really, anytime you're in a project, whether you're the facility owner, you're an engineering firm, you're a process group, you're trying to design or select, if you need a pHneutralization system, there are two primary factors that you have to understand. The first is the flow, profile of your waste, whether you're pumping your waste, whether you're going to have a gravity-based system or some combination of that, because you need to understand what your flow rate is of this aqueous waste discharge, and then also what the nature of your waste is. The chemicals that are involved in it, what type of a building it is, there's special waste constraints involved. And for this type of a conversation, we're not talking at all about sanitary-based waste. This is purely going to be process waste, really an aqueous waste-based pH system. There are some waste constituents which you cannot put down the drain, and those include solvents and things like that. That's kind of a different conversation, and we do actually have a webinar that addresses solvent handling. If you have things like isopropyl alcohol, or if you're in the semiconductor industry, some of the different SOC or spin on glass processes, that's kind of a different application. Here we're really talking about aqueous waste and really what that means. So I'd like to start the conversation just with a basic understanding of what the pH scale is, really what pH is in general. And pH scale runs from 0 to 14. 0 to 7 being acidic, really 8 to 14 being basic in nature. And you can see here there's a couple of common household ingredients: lemon juice, soap, bleach. You can kind of see even things that are common in your house, they do fall, definitely away from neutral. And, these are acidic or basic for various reasons. But what's important to understand about pH system is the logarithmic nature of it. And the further you move away from neutral, you're really increasing your relative waste strength by orders of magnitude. So 6 to 5 to 4 is 10, 100, 1,000, 10,000 times more acidic or more basic. And this plays a lot into the nature of waste and understanding that, you have a system, you have a waste profile where you're going to be down in the pH 3 range or the pH 11 range is different from a system which can be treating pH in the 1 range or the pH in the 13 range, just because of how the relative strength works. It's also important consideration when talking about the chemistries that you utilize to do pH neutralization. Discharge limits do vary, across the country, but predominantly most are going to fall in the range of roughly 5 to 9 or 5 to 10 is generally what the local municipality is going to want to see for the actual discharge from any pH neutralization system. And there are two sort of super classes of pH neutralization systems. You have passive systems and you have active systems. Passive systems, if you're familiar with the technology, are essentially like a limestone chip tank, whereby you have, a series of rocks in a tank. You pass your waste over it. It's allowed to neutralize and allow the discharge out of your system. It's a very old technology. It's not highly utilized anymore, by and large, simply because it does have a lot of limitations. It can only treat basic waste. It has no ability to treat it can only treat acidic waste. It has no ability to treat basic waste. And it only covers a very limited range of the pH scale because you are utilizing a weak chemistry in that case. Active systems, which are what encompass majority of the systems which we're going to talk about today, which are more commonly utilized in the industry, rely on real-time chemical data, within your system, and they inject a pinpoint amount of either acid or base to allow you for proper treatment. And how we kind of do that and design that is what we're going to really talk about today. But it allows you to neutralize across the entire pH spectrum from 0 all the way up to 14. That gives you obviously the full range of where your waste profile could fall out. There are three primary types of pH neutralization systems. You have the flow-through system, the batch treatment system, then you have what's referred to as a hybrid flow batch treatment system. Flow-through systems are what most people think of when they think of a pH neutralization system. You have a tank or a series of tanks, and your waste is allowed to enter. It's neutralized and flows out in a steady state rate equal to the amount of influent that you're putting into the tank. And within that basically treatment window, in that tank, you are going to neutralize your waste. It has the advantage of having a lot of a very high throughput for treatment. It does have some disadvantages. It doesn't really allow you to slow down or change the flow rate should you have an out-of-spec condition. Batch is obviously the opposite of a flow-through system. In a batch treatment process, the waste enters into the tank, the influent is shut off, the effluent is shut off, and you treat your waste volume until it's fully neutralized. Batch has the advantage of obviously being able to treat any waste stream. And if you have very specialized waste streams, or if you're trying to tie the pH system into other treatments, such as effluent decontamination or a precipitation process, if you're treating, for example, like HF, for example, batch is predominantly where you're going to be because you have a much longer and much more, reliable method of treatment in those cases. The downside is batch treatment processes greatly reduce your throughput. You have a fill time, a treatment time, a verification time, and then a pump down time to allow for treatment. And then, in this case, it could take about an hour plus to neutralize a single batch. So if you have a 500-gallon tank, you're going to treat 500 gallons per hour, whereas your 50 GPM flow-through system is going to treat 500 gallons in 10 minutes. So that's really the difference between flow-through and a batch treatment system. To compensate for this, people have developed what's referred to as a hybrid flow-through batch system. In a hybrid flow-through batch system, waste is allowed to enter into the tank, and during normal operation, you operate the system as a flow-through system. And when you have that condition, which then dictates you to go into a batch mode, you have the ability to shut off the effluent, continue to neutralize the waste, hold the waste and not allow for out-of-spec discharge, and then once you're back in spec, allow that discharge to flow naturally. And whether that's part of the actual tank or that's part of a diversion tank or an equalization tank, which we're going to talk about here in a couple of minutes, that's probably the most common form utilized in most industrial applications, say a pharmaceutical or semiconductor or something like that, because you have the ability to treat a very wide range and a very high throughput with very high reliability like you would have in a batch style treatment system. Regardless of the type of system you utilize, whether you use a flow through, a batch, or a hybrid system, all pH neutralization systems have certain components in common. Treatment tanks, they have agitation, they have chemical injection, they have controls, and then they have some form typically of effluent monitoring attached to them. The treatment tanks in the pH neutralization system are designed as continuously stirred tank reactors. And what that means is the waste coming into the tank is subject to what we refer to as residency time. and as the waste comes in, it's allowed to then cascade out. And you have agitation in the tank that allows you to basically create what's referred to as an ideal solution. So within the actual tank, the pH is uniform, and you're injecting your pH, you're injecting your chemicals in there to allow you to basically treat the volume of the tank as it has flow coming in or coming out in a steady state. And the typical residency time for pH neutralization system is 20 to 25 minutes. It can be upsized to 30 minutes as well if you have more stream waste conditions. And because of that, pH neutralization systems are typically sized for the maximum flow rate that you could see into them. Now, when we say continuous system, or even a hybrid style system, the waste does not have to be continuous all the time. So you may see peak flows of 50 GPM, then drop down to 30, 0, 10, back up to 50. You're going to have a 50 GPM system at that point. And really, when people ask me what's most critical in a pH system, whether it's having a consistent waste profile or consistent flow rate is by far and away the more important factor than actually the nature of the waste. You can adjust the chemicals a lot. You can do a lot of turn down in them. Having a fairly consistent flow rate into your system is actually very beneficial. And the residency time is really there to kind of help catch those fluctuations in the overall flow rate. The rate of mixing, obviously, we'll talk about that in a moment. And the material is like material compatibility. You are dealing with acidic or basic chemicals. Majority of pH neutralization tanks are going to be thermoplastic. They're going to be stainless steel. They're going to be some kind of a corrosion-resistant material, possibly fiberglass if you have a high-temperature application in those cases. Looking inside the pH tank for a moment here, you can see my mouse here. This is what they look like in the inside. This is the inside of a cylindrical treatment tank. You have your agitator here, and your agitator is typically sized for about 1.5 to 2 tank turnovers per minute. So it's not very high agitation in most cases, but it is a moderate amount of agitation. And the important thing is you have your waste coming in through a down pipe, which goes right into the mixer backwash, and then you have your chemical injection here. So basically, you're injecting right into that point of mixing at that point. Looking at kind of a cutaway of a 3D model, you can see something very similar. The waste comes in, is directed to the bottom of the tank, goes into mixer at that point, and then essentially is allowed to flow out in most of these cases. When you can comfortably treat about 2.5 to 3 tank turnovers, there are 2.5 to 3 pH units in a single pH neutralization tank. Sometimes you do end up putting these tanks in series at that point, barring other outside considerations for treatment. Moving beyond the pH neutralization tank, you do have your chemical injection. And this is really what you're injecting to neutralize the waste coming into your system. Again, looking at the pH scale from before, you have a pH range of, say, 0 to 14. Realistically, most pH neutralization systems operate in the range of, it's really 2 to 13, 1 to 13. Once you get kind of beyond 13 to 14 or getting a 1 to 0 range, you can treat it, but you obviously have to treat it as a special waste consideration. And by and large, the chemicals that you utilize in your system are significantly stronger than your waste stream. The most common reagent chemicals utilized are 50% sulfuric acid and 25% sodium hydroxide. And the reason for the reduced sodium hydroxide, it really has more to do with its chemical nature, particularly if you're in a colder environment. You don't want to have any kind of crystallization in your lines. Sodium hydroxide will turn into a jelly-like substance at around 55 degrees. These chemicals are injected in a much, much lower range than what your waste stream is. So where you may have 50 gallons per minute flow, you may have 5 gallons per hour of your chemical injection. And that's because these chemicals are going to be, based on the pH scale, orders of magnitude stronger than even your strongest waste stream. These chemicals are obviously hazardous, so they do need to be stored and contained properly. This typically involves having segregated 110% double containment of each chemical individually. You also need to segregate the metering pumps from each other, and you need to have double contained lines for these because this is where you're really going to be handling the most or the highest level of chemistry in your system.
Mark, we do have a question about chemicals. What are the pros and cons of onboard reagent tanks versus utilizing chemical drums?
Thank you, Michael. Yeah, so one of the things that comes up quite a bit, and you can kind of see here in the picture I'm showing here, these are actually chemical drums, which are basically on board of a system. So, in a pH system, you have a tank, you have your reagents, and one of the things obviously is your chemicals are going to be consumed as your system operates. So do you want to have onboard tanks that you then fill, or do you want to wheel up a drum every time and basically put it in place? And a lot of that really has to kind of come back to which is really an owner preference. How do they want to handle the chemical? There is no fail-safe method. No matter which way you go, you do have to handle chemical one way or the other. Whether you're filling a reagent tank, you're going to have some kind of a drum or a built-in pump, which is going to pump out of your current tow or chemical or drum into these tanks. If you're replacing drums, now you're basically bringing up a drum, you're pulling the suction wand, you can see here, out of your system and then placing them in place. Me personally, I think it's better to go with onboard chemical tanks and then have a chemical or trusted supplier actually just come and deliver them. They have the proper equipment rather than having the facility themselves wheel drums in and out of the actual system and then do the actual chemical handling. It really takes up the same amount of space overall in the system. But your chemical tanks here, they're fully contained. You don't have to worry about using things like pallets or other equipment like that adjacent to your system to then locate your drums on or lift the drums into the actual system at that point. Talking about controls for a moment, because this is really how you tie in. Obviously, everything you're doing in a control system for pH is going to be related to how you're controlling your chemical injection to then neutralize your waste to meet the pH set points. And all pH systems operate in what's referred to as temper proportional control. And you can see here, most pH systems do operate obviously on a PLC basis. But what's important has to really do with the chemical injection and the feedback you get from your pH probes in your system. This is the pH scale we talked about earlier, from 0 to 14. And when you're kind of out here in the more extreme waste ranges, you can basically run your metering pumps at a fairly high flow rate at that point. And as you move closer and closer to neutral, your metering pumps basically need to turn down proportional to the pH scale. So within your treatment tank, you have a pH probe, you're monitoring the pH. As you get closer to 7, say around 3, you're going to start to turn it down to 10, 100, 1,000 to 1 to effectively match that pH scale. And this goes in both the acid as well as the caustic direction at that point, which is why almost all pH systems are two-way adjustments. You can see here, this is just a gentleman cleaning off a probe. Probes are a bit of a consumable in the system, and they do need to be calibrated fairly frequently. And there are a lot of different types of pH probes out there. These are typically located in each of the treatment tanks as well as the effluent. And obviously without that, all the tanks, mixers, metering pumps, everything really functions based on the readings coming off of a very simple pH probe at that point. So it's very important to really maintain those within your actual system. Not directly related to pH systems, but kind of, in addition to them, we have what's referred to as equalization tanks. I talked earlier about how equalization tanks are often utilized. How you would generally have a preference to control flow into your system, say over your pH coming into your system. That's what equalization tanks let you do. They're very important when you have very high discrepancies between your high flow and your low flow conditions. So whether your system is operating, say, majority of the time at 150 GPM, then you have a spike to 300 GPM, you can equalize that in your tank to run it at a lower flow rate. It does offer a little bit of self-neutralization, but again, based on the pH scale that you have, one waste is 12 and one waste is 5, you're going to end up with mostly just 12 waste because obviously the logarithmic nature of pH, you need a lot of waste to basically get some kind of dilution effect going. So by and large, dilution is not the solution when it comes to pH neutralization systems. It's also very critical in a batch process where you need this tank upstream of it to allow you to transfer your batches into your system for treatment at that point and then hold the incoming volume until you're ready for the next batch treatment. It can also serve in a hybrid system as really your out-of-spec tank for those types of systems. So equalization tanks, the more sophisticated your waste treatment system or waste profile is, the more important it is to have an equalization tank upstream of it. It's also important if you're talking about thermal waste, if you need to collect waste that may be hot and then treat it for thermal conditions before going into or lowering the temperature before going into your pH neutralization system. We're going to do the first of our polls now, for those who are interested in asking them. And we'll give you guys about 30 seconds to answer them, and then we'll kind of discuss it. All right, thank you. Again, the poll question was, treatment tank sizing is based on which of the following flow rates? Average flow, daily flow, max instantaneous flow, or 25% more than the max instantaneous flow? And the answer is the max instantaneous flow. You need to size it for the ability, you need to size it for treatment to allow you to basically size it for your worst case scenario coming into your system. That's because even if you size it for an average flow rate, it's when you have that higher flow rate that you run the risk of having the out-of-spec condition. And obviously, out-of-spec conditions, when it comes to treatment systems, that can be very detrimental. That could really define in other types of situations. If you do obviously project to have future capacity needs, you can oversize the system a little bit. That's obviously a discussion you need to have about thinking about long-term maximum waste profiles. That's kind of a segue now into how we really size pH neutralization systems. We talked a little bit about the nature of pH, talked about some of the components that are involved, the types of systems, how to control them a little bit. But now the question becomes, okay, I have a process. How do I actually design a pH system? What are really the important things? And there's really two primary components to that, which, we can talk about in great detail. We're going to kind of just cover them kind of briefly today. But obviously, if there's any questions, we can certainly go through it or go through more individual applications. And that is understanding what the nature of your waste is, and then understanding what your nature of your waste, what your flow profile is. So the nature of the waste depends on a lot of things, whether it's the type of lab you're in, or facilities of biology, is it chemistry, animals, manufacturing, clean rooms, aerospace, pharmaceuticals. Really, they're all going to have a different kind of waste stream. Whether you have a boiler which are going to be cracking, and they're going to have a lot of, so that's really one of the things that comes into play. It's not always obvious what the waste profile is. A lot of times people will get a list of chemicals, for example. This is everything we have on site, but we only use X, Y, and Z in some very small quantities. Or maybe they're a pharmaceutical and they're dumping CIP waste on the drain continuously with like Wi-Fi water. These are the kind of things that you need to understand, or we can help you understand to really allow you to understand how much more capacity or what type of system or sizing you want to look at with the type of system. The other thing is the presence of high purity water or alkalinity implications when it comes to a pH treatment system. And alkalinity is one of those things which is a little bit hard to understand. So if anybody who works in the realm of high purity water knows when you're making high purity water, this is Wi-Fi water, or RODI water, or ultra pure water in those cases, the processes that you're going through, RO, deionization, you're taking all the mineral content or majority of it out of your water. So that when you use that in a process and it mixes with a chemical, when you dump it down the drain, you now what's referred to as low alkalinity waste. And this is very true in things like Wi-Fi or have Wi-Fi stills, pharmaceutical industries, also ultra pure water, and semiconductor industry. There simply is no buffering capacity for your system. So what happens is your reagent chemicals, when you go to treat this waste, they overreact in your system. And you can get these, what happens is rather than getting a nice linear curve, which you want for treatment, you get this kind of weird, oscillation going back and forth, where basically your chemicals are overreacting. So as you get closer to neutral, you're basically shooting up, well above your actual target set points. And the only way to really counteract that is with adding a buffer to the system, some way to actually re-add alkalinity back into the system. And that typically is a bicarbonate addition. Bicarbonate has the ability to buffer in both the acidic as well as the basic direction, that allows you to get the nice smooth linear curve that you want for treatments. To kind of show a real world example, this is some actual chemical data from a titration curve. And this is generally what you want from different set points when you're doing pH adjustments. It's a nice kind of linear set point going down from, say, 10 with jumps, based on concentration, down to 7, and then continuing onward. This is what you see when you have alkalinity waste. You see you have the same set points here in the lower range. Once you get closer to 3 to 4, it jumps all the way back up to 10. And if I added then acid, in this case, it would do exactly the same thing. This is why it gets very hard to treat low alkaline waste. You're going to see this very high jump essentially between one set point and another, and you need to really buffer that to kind of get this sort of pink curve here is really what you want to see in most pH neutralization systems.
Mark, regarding buffering, do you need to add buffering in a pH monitoring system if the waste is predominantly neutral?
So that's a good question that comes up. Sometimes you don't actually need to have monitoring. Sometimes you don't actually need to have a full-blown system. So one thing that comes up is if I'm really using my pH system mostly for monitoring and not really for treatment, do I really care as much about alkalinity? And the question is, yes, you do. Here's one of the reasons why. Alkalinity, one of the things that has to do with how a pH probe is made. pH probes are obviously based on the idea of they actually have
Mark, it sounds like your audio has cut out.
Sorry about that, everyone. We had a little bit of an audio cut out there. I hope everybody can hear me now. What I was saying was obviously obviously in an ideal situation, people want to go by gravity into their pH neutralization system. When that's not possible, they do make what's referred to as lift or transfer-based systems where you basically collect your waste and then you have to pump it into your system. And this can happen for a number of different reasons. Obviously, waste lines by gravity, depending on what your processes are going to go underground, for example, or you might have an addition or a laboratory added into your facility or a new process, where it's just not feasible to have that gravity flow going into your actual pH system. So very often people will utilize a lift-based system in those cases where you collect it in more of an acid-resistant or corrosion-resistant lift station and then allow you to transfer it into your actual pH neutralization system. Where that's a simplex-based design. Simplex tends to be utilized more for smaller applications, laboratories or single sink applications. Duplex you see more when you're talking about an entire building. It's very common, for example, to have an application where you will bring all of your waste to a central duplex lift station point and then pump it up into a pH system if your gravity lines are underground, for example. That's because you generally want your pH system not in a pit. You have chemicals, you have probes to calibrate, you have control systems. So ideally, you don't want that stuff below ground where you have a confined space entry in those kinds of situations. You generally want to put some kind of a lift station that allows you to control the flow then into your system. It can even act as kind of a quasi-equalization tank at that point to then feed into your pH neutralization system. So when developing a flow profile, you're going to look at a lot of different things. You're going to look at everything's going to be dumping into your pH neutralization system, and then everything's going to be dumping into a lift station based system, and how those two combine to essentially transfer into your actual pH neutralization system. And if you have specific processes, if you have a tool machine that dumps continuously, or you have a process kettle, things like that, that's where you can really determine what those flow rates are. Obviously, based on, in a more industrial setting, this is what we're dumping, this is what we're actually utilizing. In a lab-based environment, it's a little bit different, where you have, say, sinks, for example, and you have cage washers or autoclaves or dishwashers or RO or point-of-use generators going on, and how they dump into your system. It's not going to be in operation continuously. So you do want to apply a certain amount of diversity factor to those. If, say, you have, a college lab application, you have 150 sinks. You're not going to see 150 gallons per minute. You might see 20 gallons per minute as like a maximum flow case in those types of situations. When doing lift stations, obviously, because how lift stations are designed, they need to account for 100% of the flow rate coming into them. You cannot apply diversity in those cases. Diversity is really a factor which is also kind of caught in the residency time. So, for example, you do have more flow than you anticipate. You do have that residency time factor as part of your pH system to allow you to do that treatment. So just some assumptions here you can kind of utilize if you're looking at, say, like a lab-based application, lab sink, some 1 GPM, a cup sink, half, fume hoods, a quarter, and then actual usage is going to be 20 to 30% diversity in those cases. So walking through a quick example here, if I had 80 lab sinks, 5 glass washers, and 10 autoclaves in a lab space environment, I could develop my flow profile based on what gets pumped and what gets in, and then do that based on 1 GPM times 20 GPM, 2 cage washers at 16. I have a total pump flow rate of 36 gallons per minute. Lift station sizing, in that case, you'd have a lift station that would be 36 GPM. Generally, lift stations are sized for 3 to 5 minutes of residency time, although really that's really just to eliminate cycling of a pump in those cases. And you always want to be pumping down your lift station, so you typically size it for 10% of the actual required rate. So at 36 GPM, 110%, you'd have a 40 GPM flow out of it, and 120 gallon tank for 3-minute residency time in those cases. Looking at the flow by gravity profile, you'd have 1 GPM times 60 last week is 60 times 20% diversity is 12 GPM. Again, the glass washers assume some diversity factor of 2, and half for autoclaves. You have a total flow rate of 38 GPM. You then combine these from 40 GPM to 38 GPM, and you see you have a 78 GPM total flow rate coming out of your system. Next is to look at what your actual waste profile is and what kind of special waste considerations you have. If it's a laboratory-based building, for example, like say at a college level, you're probably saying your waste range somewhere going to be around, say, somewhere between probably 2 to about 12, and then maybe you have some high purity water present in your system. So based on that, 78 GPM, you have a 4 from neutral differential. This would be a good candidate for a 2-stage pH neutralization system, 78 times 20-minute residency time, 1,560 gallon or 2 800-gallon treatment tanks. This is kind of the basic design of sort of how you really look at and do a very simplistic design of a pH neutralization, at least from a sizing standpoint. Obviously, that depends. This is a lab environment. Lab environments have certain fixture counts that you utilize to do this. If you go into other applications where you have, more process technologies, you have different applications, you're dumping kettles or tools, then you probably end up with much higher flow rates. One thing I do want to note, though, is pH systems can get pretty big. 2 800-gallon tanks, a control-based system with panel access, your reagent injections. In this case, you have your buffer addition as well for your high purity water. The system gets fairly big, 200 inches by 7 feet. So you have a lot of tank volume going on in your system, which is why it's important to understand, what your flow profile is and not undersize it. And when looking to design a pH neutralization system, understand, what kind of footprint and real estate you're going to need to take up in your mechanical space to really account for this. Looking at a PNID here, you can see you have your lift station feeding in, you have your gravity feed, your two reagent tanks here, acid and caustic, buffer, and this is your two-stage setup with your effluent monitoring. This would be a fairly, simplistic style pH neutralization system. At this point, we're going to do our second poll question. If you guys want to participate, again, I'll have 30 seconds, and then we'll kind of discuss it. Again, participation is fully optional in these cases. All right. So the poll question was, the two steps for establishing design of pH system are, the answer obviously is determine the flow profile and the waste profile. All the other points of this are actually somewhat important. Obviously, there is ventilation requirements for any pH neutralization system. Space constraints are important. The height and chemical concentrations utilized, but really when designing the pH system, what you're looking at is the flow and the waste profile in those cases.
Now, Mark, when would you recommend changing from a single stage system over to a dual stage system?
That's kind of a good question, and it does kind of depend on what type of system you're utilizing in those cases. Typically, most people say it's based on flow rate, but it's also based on how the system is designed. Typically, smaller flow systems, if you're kind of in more of a standard chemical range, can tend to operate as a single stage system. Once you get into a certain higher, flow range, or you end up with more extreme waste conditions, you do tend to go to a two-stage system. Most people say you can generally move the pH about 2.5 to 3 pH units in a single pH stage. That being said, how you design that stage, we're going to see in a couple minutes, does make a big difference, and you can do a lot of treatment in a single stage if it's designed for that purpose in mind. So, we at Burt Process, we do have a few standard packages that we do utilize. You can see here, this is one of our standard pHx. This is designed obviously for low flow, and this is a single stage design as we were just kind of talking about. And these run in the range of like 7 GPM up to like 33 GPM. That's small. These were typically designed for smaller applications, say college labs, even bigger high schools, small research labs. They can be plugged into a 120 volt outlet in those cases. And this is really for treating your more sort of benign waste, in that 3 to 11 range effectively in most cases. And people like them because, they're designed, looking at it kind of from a lab sync standpoint, you can kind of see 100, less than 20 things, 100 gallon treatment up to the bigger ones at 90 to 110. Very effective in certain situations. All these are available in 3D models as well. And, looking just do a quick case study here, when you have 7 floor labs and 75 lab sinks, doing the same kind of calculation, assuming it's all gravity, 30% diversity, 22.5 GPM, pH range, say 3 to 11, as I talked about. And then you would have pH differential of 4 in that case, but really it's 3. You're typically trying to hit the 6 to 9 range. You'd have 22 GPM, 15-minute residency time, 337 gallons, or a 400-gallon pH neutralization system. This is kind of where you'd sort of be in the lower range of where you want to use more of a single stage pH tank. And this is what they look like. Looking at it, it's just kind of a little bit different design. You have a treatment tank. You can see your agitator and your reagent. Those are your chemical injection lines. You have your down point and drains. And then these have your agitation as well as your chemical injection and control console in the front. We also design systems for obviously much more, sophisticated waste stream. This is our assured compliance system, and these really are designed more for industrial applications, pharmaceutical, semiconductor, aerospace. And a lot of these actually are single-stage systems. The difference is these utilize a lot of technology in them, which is designed for you know, for that higher waste stream. They basically are hybrid systems. They can go into a batch treatment mode to allow for additional treatments. They also have here a recirculation pump, as you can see, where you're doing your pH monitoring in the recirculation line. You're doing your chemical injection as well, and this allows you to have that additional, basically using your waste as a carrier medium to allow you to do a more rapid chemical injection or more efficient chemical injection for better treatment. So this is how you can do it. As I said before, you can do more treatment in a single stage. That being said, these are also built as two-stage systems, as you can see here, and there are a lot of different options. They can go into these. This is the two-stage version. You can see the chemical injection up here, redundant recirculation pumps in these cases. And as a skidded design, these will operate up to around 300 GPM. As a non-skidded design, this can go up to a much higher flow rate, up to 1200 to 1500 GPM. Once you get out of that range, you're kind of getting a little bit out of a skidded design or multiple skidded design and getting into more of a plant-based system as well. But again, these also have a lot, additional diversion storage, pump lift stations, redundant pH probes. This can do temperature treatment as well with these types of systems. SCADA interfaces. These can have larger bulk storage tanks. There's a lot of different things you can add into this or really any kind of pH system depending on what your application is. And these, as a standard, we have size from 50 GPM up to 150 GPM, as well as smaller systems which are designed, not quite there yet. You can see what they look like. You have your single treatment tank, reagents, tanks on board. You can also be drums, as Mike had asked about earlier. You have your recirculation with your chemical in your pump here, and this is your chemical injection ports here into your pH neutralization vessel. From a PNID standpoint, this is your out-of-spec condition here, where you have your shutoff valve that allows you for your additional residency time in your system. You also have the ability to not have this and go back to, say, an equalization tank or more of an out-of-spec tank in those cases as well. We do also have smaller versions of the ACS 10, the ACS 25. These are designed, again, for more specialty applications or for lower flow versions where you still need to have that same built-in capacity that you have in a hybrid-based design. These can operate, obviously, in much, much smaller footprints and for a lot smaller kind of applications in those cases. Really any pH system, regardless of style, standards, they're all really customizable in a lot of different ways. I like to use the term customizable standards in most cases. Whether you have kind of a straightforward dual-stage system, you have more higher end, we have temperature considerations involved, and you have more fiberglass-based design. This is where it's really important to understand what kind of waste stream you have, what kind of footprints you have, and what your plant needs or facility needs ultimately are in those cases, because you can make these obviously customized and tailored to fit a lot of your different types of applications. You're ranging up to, say, something like an explosion-proof pH system here. You can see this is all hazardous duty. So again, it takes a lot of the same basic concepts that we've been talking about, but can be integrated. And this is actually a batch-style pH system where you have an equalization tank, a single batch-type treatment system, and this basically allows you to treat very strong waste in a hazardous-based environment. One of the things we've been doing a lot more recently, and has also come about quite a bit during the pandemic, obviously as a result of people needing to do rapid infrastructure development, as well as having the needs to keep plants in operation, limited interaction, has been working a lot in containerized pH system design, really containerized systems in general. We did a webinar talking about this about a couple of years ago. For those who are interested in watching, we can certainly link you to that. But essentially what you're doing is you're building a pH neutralization system inside of a modular, which then can be utilized and dropped on site without going through the overall fabrication process that you would do of typical construction in those cases. And clean rooms come in a lot of different styles. Whether they're kind of more modular buildings, whether they're clean rooms, portable clean room design, as well as even shipping containers in those cases.
Now, Mark, does the pH system design change inside a containerized system?
It does a little bit, as you can kind of see here just in the video that's playing, you're working now within a space which is much more confined than you would typically see in more of an open plant environment. And, obviously access becomes quite a bit of consideration, chemical handling becomes quite a bit of a consideration, as well as the ability to then service the system as well. Because you obviously, you have these large tanks, you need to be able to get them out. You can see you have roof hatches in here. So in a lot of ways, it does and it doesn't change. You can just see a couple examples here. You need to have a lot of this linear access going on. You can see the large reagents. You can see the tank here in the back. This is kind of your breakaway door. Here, the tank is accessed purely from the front and then again from the rear, as you can see in this picture here. So the overall process does not change. It's really how you actually lay out, and there are some limitations to how big you can build it depending on what size container or module that you're actually working in those cases. And you want to have access in certain areas. So like here, you have predominantly access around your reagent tanks, your control systems, and then back here where you have your actual instrumentation for calibration, and then a lot of the sort of sidewall, the tank, which typically be up against the wall, that's really within the actual body of the container as well. You also have certain things in the container itself. You have a lot of lining, you have different sensors for the leak, you have environmental controls, you have, acid-resistant lining, as well as even chemical safety showers and drains in sumps installed in these types of systems. We do have, in addition to the webinar today, there are some other technical resources. That's actually me right there talking in this video. Those of you who don't know me, they kind of go through, a lot of what I've talked about today, to kind of showing, really the inside of a pH system and how they operate. You can just see here's one of our standard systems for those of you who've never looked inside of a pH system. This is the different reagents. This is the actual, maybe it doesn't blow up here. You have your agitator up here. I think I may have gone a little bit too far. You can take a look inside. That's actually the waste profile and how things are actually agitated, just to kind of get a familiarity of really what it looks like actually in operation. One thing to look at PNIDs and photos and have me here talk about the mixing characteristics. That's really what's going on inside of a pH neutralization system. And you can kind of see how they really operate, what they look like in a mechanical space, things like that. So this is kind of there's some other resources available for those who have any questions or certainly want to check that out. That's all available for looking at as well. This is obviously a very small base system here. And then obviously this is quite a bit larger base system as well. So pH systems, again, they can range in very big complexity here. This obviously is a much larger system. You can see the amount of footprint it's taking up in this case. As you have your effluent, this is more of a hybrid-based design. This is actually rated for outside use as well. That gives you just kind of a feeling kind of beyond just what you would typically see, here as to how big, but also obviously the fact that these are still single stage, two stage, hybrid, batch style systems. They really just grow as they get more. They really just grow as they get more tailored to meet the individual client's application and the full electrical safety, plant site specs. All this can be tied into instrumentation requirements as well. This just kind of gives you guys a bit of a picture, and these are all available to be viewed on the website as well. We do have a couple of additional upcoming webinars as well. We do have one on high purity water systems, which is going to be coming up at the end of May, just before Memorial Day, if you guys have any interest in that. And then after the summer break, we have a case study webinar, which will really dive into, a full sort of process and wastewater integration project to kind of go through in much more detail some of what I talked about today and how you actually do design, of this, as well as kind of tying that into some high purity water design. Then we might have a couple of additional webinars this fall. Again, there will be a brief survey sent out. After this, we always appreciate your feedback. And at this time, if there's any additional questions, we'd be happy to answer them in the few minutes that we have left.
Mark, while people are typing their questions, we do have some that already came in. So the first question we have, based on a given flow rate, how to assume its pH, Can Burt Process calculate a flow rate of chemical which should properly adjust process water to an approved pH limit?
Yes, you can. If you can do that if you know what the incoming pH is. So, to a degree, obviously there's a simple way to calculate it. It's like if I have 50 GPM and I have a pH of 2, I can calculate here's the level of acid present at that flow rate, and here's the amount of caustic you needed to adjust that as a basic model. When you're talking about other considerations, when you have things like alkalinity coming into play and like water quality data, that can get a little bit more complicated to actually calculate to an exact pinpoint amount, but it can be modeled in those cases. But typically, when you're looking at wastewater, you're not quite going into that level of detail. You're looking at it really more from just, here's a pH differential and here's how much chemical you need to add into your system.
I believe we touched on this a little earlier, but we have a question here. What are the typical concentrations and types of acids used for neutralization? And the second part, how would you handle 35% HCl fuming?
So typically what you utilize, I would typically recommend sulfuric acid personally. And I would say typically sulfuric acid at either 50%, 25, or so. A lot of people do use 93%. People do use 35% HCl. And you really need the reason I like sulfuric over HCl is really the lack of venting requirements. Sulfuric acid has a very low vapor pressure, so you don't have a lot of venting in those cases. It really doesn't much venting cases requirement. When you have HCl in your system, a couple of things come into play as a reagent, and you can use it. It's a very strong acid, and people do use it for certain applications. What you really need to do is you need to vent your reagent tanks. Usually you need to pull some kind of a negative vent on them. You need to make sure that you may need to coat your agitator in your tank, and you definitely need to pull also a vent or negative pressure instead of atmospheric pressure vent off of your pH neutralization systems. Otherwise, in time, what will happen is your HCl is going to basically cause anything in your plant in that area to look like it's from the 1920s with that level of corrosion that can certainly build up in there. So really, it's just increasing your venting requirements for utilizing that chemical.
Could you please expand on the design considerations of the reagent recirculation loop?
Of course. So when talking about the reagent recirculation loop, what you're really doing in those cases, so there's two different ways to do reagent injection. In a lot of traditional pH systems, what you do is you have those downpipes, which I showed you, and you basically do drip chemical injections. So as your metering pump pulses, it's dripping through basically a foot valve that's going into the basically volume of your tank, which then gets caught into the mixer backwash. When you're using recirculation, what you're doing is you're pulling waste out of your tank and you're constantly recirculating it. And you're now injecting your chemical into that line. So in effect, what you're doing, you're still basically pulsing it in, but it's not so much the chemical itself, how it's injected, it's how then that waste is, and then how that stream is brought back into your tank. It's going to be recirculated back now under some flow rate, 30, 50, 100 GPM, depending upon what your system flow rate is. They're not have to be corresponding, obviously, but they do have to be somewhat proportional, and then that's being educted right back into your mixer backwash. Now you're basically blasting this larger volume now of sort of basically charged, reagent waste right into your mixer backwash, and that creates a lot of efficiency when it comes to your pH treatment in those cases, as opposed to just simply dripping into the tank. Like as I was showing you guys, that picture of the tank kind of agitating, kind of dripping into that sort of, mixing solution at that point. It's really a mixing increase. Using that basically as a carrier medium gives you a lot more mixing capabilities.
Can a single stage system be used for very acidic conditions, or would you recommend a multiple stage system?
It can, depending on how the system is utilized. So, for example, a lot of our ACS systems are single stage, and they can do that because you have that recirculation in other types of conditions. That being said, when you don't have some of those additional features, you may want to go to a two-stage system depending upon what your nature of your waste is and what your flow rate is. The bigger the flow rate, the more I'd move away from utilizing a single-stage pH system.
It looks like we have one more question here. Would you recommend providing a solids interceptor upstream of the system to prevent any glass or debris from entering the system?
Yes, I would. Very much so. One of the things you have to understand is when you're talking about pH probes is, and really for the treatment tank, if it's running by a gravity, for example, you can have a certain level of particulates coming into the tank. You'll get some suspension of it, obviously, in the agitation. It'll flow out. If you have a lot of solids or debris coming into the tank, you do run the risk of it building up. You want to run the risk of it now damaging your pH probes if it's now in suspension. It's basically colliding with them. In your effluent U-trap, for example, same situation. Now you have a concentrated pipe, for example, where you could be funneling that waste and it can build up. So yeah, if you have any application which is going to have very heavy solids or oils and greases coming into it, you typically want to have either like a solid separator or an oil water separator upstream of that to do that, to really remove that before you get to your actual pH system. I did a project years ago at a government facility, and they were dumping gorilla hair down the drain from giant cage washers, and yeah. So that gives you an idea that you can get a lot of solids as things turn black, and then now you have hair wrapped around your agitators and things like that. So yeah, there's a lot of, you definitely don't want to be doing that if you can certainly avoid, especially in glass. That's your solids concern, because you run the risk of damaging the thermoplastic material in those cases.
And one more question just came in. Do you have treatment systems utilizing bleach for tying up hydrogen cyanide?
Yes, we do. That's really like a cyanide destruct-based system, which we often tie into pH neutralization. And that's typically done as either a batch or a multi-stage system, whereby we will use, like in the oxidizer, which is hypochlorite in that case, is to turn the cyanide to hydrocyanate, then down to CO2 and nitrogen gas, and then you do final pH adjustment after that. So that's what I was saying before. We do have systems which utilize pH neutralization. Again, cyanide destruction, I don't see it too often anymore, as it used to be much more common, say 20 years ago. A lot of the cyanide has kind of gone overseas at this point, but we still do it. Same thing with like HF reduction, and even some chemical biokill systems in those cases, kind of a similar thing. They utilize another chemical in addition, and they utilize pH as part of that kind of overall system. Is that all we got, Mike?
I believe that's all the questions we have right now.
All right. If anybody has any more questions, you can certainly feel free to email us. Again, we'll be sending out a quick poll question here in a little bit. Webinar registration for the webinars is open. If you guys would like, you guys can simply follow the link. And thank you everybody for joining us today. And again, any questions, feel free to reach out. Thank you.